Alrighty, we're still in section 2.1. Now we want to look at properties of matrix multiplication. Matrix multiplication. Much is similar to real numbers with one glaring omission. So first, if we take A times B and then multiply by C, well, that's associative. So we have associativity. So not a big deal there. Now, if we have our scalar multiplication here, we could do that scalar. It can kind of go anywhere. We could do it as t times a and then multiply by b, or we could do the t times b first and then multiply by a. But notice everything is in the same direction. Now, because of that, you could also, with negatives, right? If I have negative AB, I could do that as negative A times B, or I could do it as A times a negative B. Okay, so that's just letting t be -1. Distributive property that we're used to with addition and multiplication. So if I have that, well, I could just do it as AC and then plus BC. Now, again, notice everything goes in the same order, though. Of course, now, as we do this, all these things have to be defined, right? So A and B have to be exactly the same size in order to add them. And then C has to have the right dimension to match up with the sum there in order to do the product. Okay, but as long as that's the case, we're all set. Now, what they mention in the book is, A and B are m by n, C is n by p. So notice the n's match up there, and so we could do that matrix multiplication, and since A and B are both n by n, we can add them. Okay, so you have to make sure dimensions are the same. And then 4 is just a rehash of 3, except it's from the other side. It says, now why they switched to a D, I'm not sure, but D times A plus B is equal to dA plus dB. But there is a little bit of difference here, just in that, okay, A and B, they have to be the same size again, m by n. And then D is, now in this case, it's P by M. So the M's match up because D is on the left, and so, since D is on the left, the columns of D have to match the number of rows of A and B. Okay, whereas back here, the columns of A and B had to match the rows of C because the A and B were on the left. Left and right matter a lot. Okay, now what's missing? Okay, generally speaking, A times B is not equal to B times A. So let's just, try something here. I don't know, what happens if we take 1, 2, 3, 4, and we multiply by another 2 by 2, 1, 3, 5, 8. I don't know, what do we get? So I'm doing this on the fly, so it'd be sad if it actually did work. But, right, we get 1 times 1, plus 2 times 5, so plus 10. Then first row, second column, first row here, second column there. 1 times 3 is 3, 2 times 8 is 16. And then 3, now I'm going to the second row, first column. 3 times 1 is 3, 4 times 5 is 20. And then 3 times 3 is 9, and 4 times 8 is 32. Again, practice, practice, practice on your matrix multiplication. And so we get 11, 19, 23, and 41. Now let's turn it around. Okay, so we had 1, 3, 5, 8 times 1, 2, 3, 4. And now when we do this, we have 1 times 1 is 1. 3 times 3 is 9. Right away we get a different number there. So then 1 times 2 is 2, and 3 times 4 is 12, so we get 2 plus 12. 5 times 1 is 5, 8 times 3 is 24, so 5 plus 24. And 5 times 2 is 10, plus 8 times 4 is 32, so 10 plus 32 for our dot products as we go. And so we get 10, 14, 29, and 42. Definitely that is not equal to that, okay? So you see, that is why that's missing, all right? Generally speaking, matrix multiplication is not commutative. There are cases where it is, and we will see some of those cases, but generally speaking, not commutative. Okay, and so we'll stop this video here.